Welcome everyone. Welcome to this third video on the series. Today we're going to introduce LTspice, a circuit simulator. We're going to learn how to use it and essentially how to uh, model circuits and simulate its behavior, specifically in the time domain. So we're going to focus on the waveforms that we're going to be measuring or simulating on the software, and some calculations also, sweeps of variables, very essential things. So let's start with starting a new blank systematic. So this is how it's going to look like. Again, I'm using Mac OS. If you have any other operating system, it might look slightly different and more useful, actually more useful. And Windows, you're going to have a bar with all the regular codes. But what we're going to use here, it's essentially the same in any operating system. So this time we're going to work with a very simple system. Let's start with the voltage source. So let me show you the steps one more time. You're going to right click here and we're going to go to draft and component. Or you can do F2, that's going to work too. It's going to lead you directly to this part. So then here on the search tab, you're going to search for voltage and you should see this one, right? Voltage source, which is either a DC, AC, pulse, sine, square wave. So we can select the one that we want. The circuit that we're going to be studying is going to be a very simple circuit, just to explain the functionalities of the software. So we're going to add an inductor in series. So we can search for inductor here. This is the regular one. We can select any value here. So you can do Control R, or in my case, Command R to rotate it. And finally, we're going to add a resistor. So again, we'll look for resistor. If you go to this library, you're going to find plenty of other elements that are mostly useful for power electronics, I would say. And there are many of them that are rated. So with actual values, real models. So this is very, very good for those type of applications. But in this case, we just want a simple resistor. So here we have our three components. And now we're going to connect them together. To do that, we are going to go to draft wires, and we're going to have this wired up. So we connect them all in series. Click, 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 and back to the source. One important thing in LTspice that you can never forget is the ground. To access the ground, I have to click G on the keyboard. So G, and you're gonna see this ground appear here. And now I can connect it back to draft wires, and I can connect it back to the circuit. So we're saying that this node here corresponds to the 0 voltage or the reference. Now let's add values to these elements. So see that if I hover over this element and I right click here, I can enter a DC value. Of course, this is AC, so we're going to go to Advanced, and we're going to select a sine wave. Sine wave, that's what we want. We don't want any offset. We're going to use an amplitude of 10 volts and a frequency of 1 K. This thing knows K means 1,000. It knows that 1 M, capital M, means mega, and it knows that underscore M means milli. So we're going to take advantage of that. So very simple sinusoidal waveform here. Then again, hover over this one, right click as it says up there, right click to edit. So this one is going to be 10 milli. Let's use 100 milli. Okay. 100 milli. And finally, we have a resistor that we're gonna say it's 100. So internally, the software understands that you're gonna be generating a zero offset, one maximum value voltage source of 1 kilohertz, and it's gonna be connected in series with an inductor of 100 millihenries and a resistor of 100 ohms. Okay. So now to simulate this system and see what are the actual waveforms, one thing that we have to do is to command it. So to do that, we're going to right click, we're going to go to Spice directive, and here we're going to write this little piece of code. Dot tran from transient stability or transient analysis. And the order here is going to be the first number that you're going to enter is going to be the time step. Sorry, time step. So in our case, we're going to use 1U, which means 1 microsecond. That's going to be essentially the resolution of the simulation that we're going to use. Then the second value that we're going to use is going to be the final time. So let's do 0.01. So means that we're going to simulate from 0 to 10 milliseconds with a resolution of 1 microsecond, and we're going to see what happens with the circuit. Okay, and we can put this whatever we want. Let's put it up here. So to run the simulation now, we have to click on this running guy, run, and we immediately get this pop-up. So now to get the waveforms, we're going to right click here and we're going to add traces. So what are going to be those traces? Whatever we want, essentially. So let's do voltage or current at the resistor R1, okay? And we have the waveform right there. So we can see already that there's no steady state here. It seems like after 5 milliseconds or 4 milliseconds, we actually see the steady state of the system. So one thing that we're going to do is to tweak this transient simulation a little bit because we're only interested in the steady state analysis, only when there are no dynamics. So we don't care about this initial transient. We only care about the steady state. So let's fix this up a little bit. So to do that, we're going to right click here on the transient stability, and we're going to add a third parameter, which is going to be the start of the recording of the simulation, which in this case we set after 4 milliseconds. So let's use 0.004. So we actually going to be seeing from 0.004 up to 0.01, from 4 millis to 10 millis. Okay. The other thing that one more thing, everything is going to get redistributed. So 4 millis is going to be our new 0, t equals 0. So we're actually going to be looking at a simulation from 0 to 6 milli, just to make it make sense. So if we right click here, label net, we can name this node to avoid having this this default value. Let's call it S for source, okay? S for source. And this one on the load side, let's call it L, okay, for load. So now we run the study again, right click and add traces. So what does it mean here? We have voltage at the source, voltage at the load, current at the inductor, current at the resistor, and current given by all of them should be the same. You can try that out. So let's pull both. So we're gonna have voltage at the load. That's gonna be one of them. Then we can add another plot here, which is gonna be the current. So add traces again, and we're gonna add the current at the load or the resistor R1. So one thing that we can see immediately is that both waveforms are in phase. That makes sense. Voltage and current at the resistor should be at the same phase always. If you look at the voltage at the inductor, which would be the voltage at the source minus the voltage at the load, this voltage at the inductor and the current at the inductor should be 90 degrees apart. So the current should be lagging the voltage at the inductor by 90 degrees. You can try that out by yourself. So now another thing that we're going to introduce is the multiplication. So we're going to add another plot, third plot, which is going to correspond to, traces here, the instantaneous power. So to link with the previous video, we're gonna now simulate, or we're gonna calculate what would be the instantaneous power on the circuit. So for that, we're gonna do simply the multiplication. The current at the load times the voltage at the load, okay? And we should see this double frequency waveform, right? We have that. We know that the average of this signal corresponds to the average power, or what we're going to know as real power. Let's add some grid here. And now to tie this analysis to what you're going to be doing on lab 1, let's add two more things. So this is the simulation of one particular case when you have just one value for each parameter here. But we can definitely sweep different values. So let's say we would like to simulate 10 different cases with 10 different values of this resistor. To do that, what we have to do is to right click here, and instead of put a definite value, we're gonna, in this curly brackets, we're gonna select a name. Let's say R load, whatever name you want. R load, and now it's a parameter that we can vary. So to get different values for this R load, we're gonna right click here and we're gonna do another command. So this command is gonna be dot step. So what we're gonna do, the syntax here, step parameter, we already defined the parameter. What's the name of the parameter? R load. And we're gonna sweep it from, let's say, 100 to the, let's say, 1000 in steps of 100. That's what I'm saying. So step is to invoke this function of sweeping the value of a parameter that it's called our load from this value to this value in steps of that. So that's the syntax here. We click here. And now if we run the case, you're going to see that we're going to be running 10 simulations and all the results are going to be showing on the waveforms here. So we know that the voltage is increasing or decreasing depending on the value of the load resistor. Same with current, and of course, power. Power is going to change most definitely depending on this resistor. So now in terms of measurements, so one thing that we would like to have here, it's the average value of this signal. So for each value of R, it would be very helpful to have the average power. So one thing that we can command here, let's add another command here. Third of this video is going to be mesh from measurement. So measurement, it's another special command that start with the name of the measurement that I want to define. So let's say it's going to be P, or the average of the average power of the load, P load. Now the command to calculate that average is going to be simply average of what? Of the voltage at the load that we called VL times the current at the load that we call IR1. Okay? So that's how the software understands that you're calculating the average of this expression. This calculation gives us this waveform, and we're taking the average, and that is going to be one singular value, right? This is steady state, so that thing is going to give us one singular value. Okay, so let's put it somewhere here, and then we can run it again. So now we have the exact same waveforms, but we can right click here, view error logs. The logs are going to tell us whatever measurement we have. So in this case, this up here, this thing is saying, okay, you used 10 steps from 100 to 1000 in step of 100, just as we said. And also for each step, you're going to be looking at P load, the measurement, P load. So let's modify this. Measurement below the average. So I got one thing wrong. I said AVR, but it's actually average is AVG. So that's on me. Let's do it again. Run it again. It didn't make sense that we had all constant values. So sorry, view logs, and now we're talking. So the average, see, that's the expression for that measurement value. So we have different values of average power at the load. And we see that for our load equals 100, we have 0.012 watts. And then we're increasing the resistor load, and the active power, or the average power in this case, is increasing up to some point that around this value, around 600 and 700, we reach maximum, and then the powers start decreasing again. So it seems like around these two values for this particular circuit, there is some special value of R that achieves maximum power from the source to the load. So this might be helpful for you for Lab 1 activity. You can definitely use a simulated tool to come up with a theoretical solution or explanation of what is happening with the circuit, but you definitely have to test it too on the kit. So that's very much what I had for today. This is going to be, again, very helpful for all activities related to time domain signals. And later on, we're going to explore other functionalities which are related to frequency domain signals and how to study those on the software. But that's for the following videos. I hope you like it. Thank you.